SwayamPrabha. Digital India. Educated India.
Welcome to week 7. In this week we will discuss about analysis of composite laminates which can have piezoelectric patches in it. So, we can have a composite laminate or we call it a laminated composite plate which has several layers of plies, and then it can have composite patch. This patch can be localized in a single region or it can be distributed all over, it can be at top, it can be at bottom. So, composite patch also becomes one more layer to it. So, we will see how we can analyze such laminates. Now, to do this, at first we need to see the governing equation of composites. So, to derive the governing differential equation of composites, we can do it in two ways. We can take a small part of the composite laminate and we will do the force balance, or we can start from the energy equation and from the using the variational principle we can find out the governing differential equations as well. Here we would look into the force or moment balance approach to find out the governing differential equations. So, let us imagine that we have a one small element of the entire composite laminate, and this looks like this. So, let us denote this as my x axis, y axis and vertically up z axis, and this small part can have a length of delta x, this can have a length of delta y. And this laminate can be subjected to various in plane and out of plane forces also. So, in plane forces, in plane distributed force, let us assume there is Px, and let us also assume that there is out of plane distributed forces which is we call Py, and then there can be vertical forces distributed, vertically a force along z direction, and let us call it Pz. Now, let us look into the stress resultants. So, this face can have a normal force Nx, this face can have normal force Nx plus del Nx del x by del Nx by del x multiplied by delta x, and similarly this face can have Ny, and this face can have Ny plus its increment which is this. So, these are the normal forces. There can be shear force. So, this is our shear Ns, and here it is Ns plus the increment. Similarly, here we have Ns and here we have Ns plus the increment. Now, let us show shear forces. So, the shear forces I am using a different color. So, shear force vertical Vx. So, it is a shear force in either xz or yz plane, which we are calling Vx and Vy. So, this can be Vx plus del Vx by del x multiplied by delta x, and similarly here also Vy, and here can be Vy plus del Vy into delta y, and at the same time this there can be stress resultants in the form of bending or twisting moments. So, to denote the moments we would use arrow with a double head, and this would follow the right hand rule. So, if we so a moment like this, which is denoted by a arrow which is in this direction, denotes a moment like this. So, if we see from this side, the moment is a anti-clockwise moment. Now, if you want to draw the bending and twisting moment for these cases, so if we draw mx, the mx would look like this. So, this is mx. Again, please understand, as was said before, this mx it acts with respect to y axis, but because we get this moment mx by integrating sigma x after multiplying with z, we call it mx. And similarly, we have mx plus del mx by del x multiplied by delta x. Similarly, there can be my, and my is at this phase is my at this phase is okay. So, in this case the direction of the arrow is this. So, this is our my, and in this case the direction of the my is my plus its increment del y multiplied by del y, and then we have the moment ms, that is a twisting moment, and the twisting moment is this one ms, and then we have ms plus delta ms by delta x del x multiplied by delta x, and similarly there can be ms here, and there can be ms plus delta ms by delta y multiplied by delta y. Now, we can look into the equilibrium of this entire system. So, if we do summation of all the forces equal to 0, that would give me this equation del n x by del x plus del n s by del y plus p x equal to 0. Similarly, if we do the summation of forces along y direction to be 0, that gives me del n s by del x plus del n y by del y plus p y to be 0, and then if we have summation of forces along z direction to be 0, then we get del v x by del x plus del v y by del y plus Qz to be 0, and then if we take bending moment 0 anywhere. So, we can take bending moment with respect to y axis. Let me write moment w with respect to y equal to 0, and then that gives me del mx by del x plus del ms by del y plus v x equal to 0, and similarly along y axis we get del ms by del x plus del my by del y plus v y equal to 0. So, this we can call equation 1, this we can call equation 2, this equation 3, then we have 4, then 5. So, combining 3, 4, 5. So, 3, 4, 5 in combination gives del 2 mx by del x 2 plus twice of del 2 ms by del x del y plus del 2 my by del y 2 minus pz equal to 0. So, this equation 1, 2 and 6 are our governing differential equations. Here we have the vertical shear we have eliminated, because we are combining equation 3, 4 and 5 and we are getting a new equation 6. So, in terms of the stress resultants nx, ny, ns, mx, my and ms, we have these 3 equations, equations 1, 2 and 6, which needs to be solved to find out the behavior of composite laminate. Now, we will solve the laminate problem using various methods. Now, we will solve these laminate problems. So, these are the governing differential equations, and we already know that for composites we have ABD matrices that relates our strain components in terms of the stress resultants. So, we will substitute those relations in place of nx, ny, ns, mx, my, ms. And also if we assume that there are piezoelectric materials and it is under induced strain actuation, then we get forces like nxp, nyp, nsp, and which we need to incorporate, and we can write the equation in this form. So, this equation becomes this. So, forces corresponding to free strain are our nxp and nsp, and similarly we will have nyp and mxp, myp and msp. Now, when we have composite laminates with piezoelectric patches, at the top or at the bottom. So, depending on how many patches we have. So, this patch tries to expand or contract. So, previously for the beam problems we had only the expansion or expansion or contraction only on one direction. Here it can have this x y in both the directions, and accordingly it induces both block force in x direction, y direction, as well as shear block forces, and accordingly it can induce bending moments in mx, my, and also in ms, a twisting moment. So, the expressions for nxp and nyp, nsp we will see it later on. So, just now let us assume that there are piezoelectric patches and we know the expressions for nxp, nsp and nyp, and if we know them, they are accounted in the differential equation in this form. So, we will see these see what nxp, nyp, nsp are in terms of the free strengths later on. So, the first equation becomes this, the second equation becomes this after we substitute nx, ny, ns by the relations that we get in terms of AB matrices, and the third equation is this. So, all these equations, so initially all the equations were written. So, these three equations are written in terms of the stress resultants, and finally these equations are written in terms of the displacement components u0, v0 and w. So, this previously for a beam problem there could have been an extension along x direction and there could have been a bending. So, extension along x direction, a pure extension we defined as u0 and vertical displacement due to bending was w. In this problem we have u0, v0 and w because there can be extension or contraction both in x and y direction, and there is a w, the displacement along the z direction. So, we can call it mid plane displacement along x, this is mid plane along y, and this is vertical displacement. Now, let us write this entire big governing differential equation in a much shortened form. So, here we are defining a matrix of operators and we are defining each operator by this symbol double stroke D. So, du1 means this. So, when du1 operates over something, so if I look at this entire matrix multiplication, this, so here we should have u0 and v0. So, u0 gets multiplied with du1 which means u0 is operated by this double stroke du1. So, this becomes a xx multiplied by del 2 u0 by del x2 plus 2 xx multiplied by del 2 u0 by del x del y plus ass multiplied by del 2 u0 by del y2, and accordingly dv1 is v0 is operated by dv1. So, the operator is here and w is operated by dw1 in the first equation, and likewise all the operators are defined here and they can be written just by looking into these equations. And these are the right hand side terms. So, these are the corresponding force terms that comes due to the block forces and moments from the piezoelectric patches, and we will define this in terms of the free strengths later on. Now, to apply the Galerkin technique, let us imagine that our u0, so these are all u0 because these are the mid plane displacements. u0 is a weighted combination of these basis functions. So, you have phi uj which is a function of x and y multiplied by q uj, and then we sum over 1 to m. So, m is the number of terms which is used to approximate u0. Similarly, v0 is weighted combination of this function where the weight is q vj and these are the unknowns. N is the number of terms to approximate to v0. W is this likewise, and P is the number of terms to approximate W. So, our unknowns in this problem are QUJ, QVJ and QWJ. So, we can write this in a much shortened form as this, where our capital U matrix, capital U is U0, V0 and W. So, we write this as phi U1 up to phi Um, then all zeros, then we have 0 phi V1 up to phi Vn, then all zeros, and then we have zeros here, phi W1, phi Wp, and this gets multiplied with QU1 up to QUM, Q V1 up to QVN and QW1 up to QWP. And this entire thing we write as a big phi matrix multiplied by Q. So, if we use the symbols for matrix and vector, this looks like this, where phi is this matrix of these basis functions phi's. So, now rest of the procedure, as we discussed for 1D problems, we follow the similar procedure, and so we define an error function, and the error function is, if we go back to the actual equation, error function is just this, we subtract the right hand side from the left hand side, and ideally it should be 0, but because our solutions are approximate, there is some error, and that is our error function. So, let us define this this matrix as a operator matrix D, and this we have already defined as U, and let us define this as a matrix FP maybe. So, our finally the error function looks like this double stroke D matrix multiplied by U minus Fp, and this error function is nothing but again D. For U we substitute this phi matrix, then we multiply this Q minus Fp. So, this is our error. So, let us define it as this epsilon, and then what we do is we multiply phi j transpose. So, the jth phi, and we transpose it, and then we multiply with the error epsilon x y, and then we equate that to 0, and we do it for each and every j. So, there are total m plus n plus p number of those j's, and that will give us m plus n plus p number of equations, and we have m plus n plus p number of unknowns. So, finally, so here we do it j is equal to 1 to m plus n plus p, and then finally we have, following the same procedure that we did for the two one dimensional cases, we get the same similar kind of matrices and vectors. So, here our k I j is phi I transpose, and then we have that operator matrix which we already defined in a much shorter form. So, let us use that instead of writing the whole matrix. And then this multiplied by the phi j vector and integrator omega. So, here we are integrating over omega. So, omega means the domain of the entire surface. So, if our piezoelectric laminate is like this, so if it goes from x, y, z, if we just look at the 2D surface of it. So, if it goes from, suppose its dimension is a, here the dimension is b. So, here omega would mean the domain spanned by it is spanning from 0 x equal to 0 to a and y is equal to 0 to b, and again it need not be a rectangular or square, it can be any curved domain also. So, omega takes care of that. So, omega is the 2D surface, because we have already written the governing differential equation in terms of 2D. We have already get rid of the third dimension, because we are already we already wrote it in terms of nx, ny, ns, my, ms and mx. So, those had the stress components integrated over the thickness. So, the thickness is not coming into picture. So, here we are dealing with only the 2D surface domain of it. Just like that, for a beam problem, we got rid of the thickness by integration and we dealt with the governing differential equation only on x axis. Here it is spanned by x and y axis, and that is our capital omega. So, accordingly we can now write f p I, the ith component of the force vector, which is f p. Omega. So, this gives rise to total m plus n plus p equations, and by solving this m plus n plus p equations, we can get those m plus n plus p number of q's which are the unknowns in the problem. Once we get those m plus n plus p number of q's, we can substitute back and find out our u0, v0 and w, and that solves the problem. So, here the only thing is that we have not defined our nxp and nxy, nxp and nxyp and so and nyp yet, which we will define in the next class. Now, here please understand our nxyp is equal to nsp also, and mxyp is equal to msp also. So, we would mostly use the notation where we would denote this as ns or ms instead of nxy or mxy. So, with this I would conclude this lecture here. In the next lecture we will see more into this analysis. Thank you.